Hello, everybody. In this video, we're going to start the second part of the chapter where we are going to talk about the flow sheeting and how we can draw a proper flow sheet. What are the things that we need to keep in mind while we are drawing the flow sheet? So we will start with the main motivation behind using or drawing flow charts or flow sheets. And the main reason is that and of course, we know that the flow chart, we have already discussed them before in the few problems that we solved. And we said we know that the block diagram or the flow chart is a block diagram where we show the steps of a process in a sequential order, and it's a tool that we use to make the problems easy for us to understand and to make the problem clear regarding the steps and what happens in each one of the steps. It also includes a lot of details about the parameters that we are interested in that we show on the diagram as well. The flowchart will summarize a lot of data since we need to describe the process in a lot of text, while the flowchart will include all the details and all the descriptions in just one place. And it's well known that the picture is worth 1,000 words. It can summarize a lot of things in just a small space. So let's take this example that we have here for a flowchart. We will read it and we will try to convert this text that we have here into a diagram. So the process is starts with a gas flow that contains nitrogen and oxygen. So it's a stream that contains oxygen, nitrogen, and we combine it with propane in a combustion chamber. So there is a combustion chamber. We don't know how it looks like or how it is designed, but we know that there is a combustion chamber, and we have some of the oxygen and propane react. So it's not all the propane and oxygen react to form carbon dioxide and water vapor. And then the product is then cooled in a condenser to condense water and separate it as liquid stream, while the rest of the gas components are produced in the gas stream. So it seems that we have two units. One is the combustion chamber, and the other is the condenser. So this is what we have. We have two input streams to the combustion chamber. One is propane and the other is oxygen and nitrogen. And then the products will be all of these five components. I would expect that the propane and oxygen would be consumed and we'll have carbon dioxide and water as products with nitrogen because it's not reacting. But this is not the case, and we know this because we are told that some of the oxygen and the propane are consumed in the reaction, while the rest is not. So this is what we have in the product stream, which is fed to a condenser. And no matter what happens to the condenser, it's just a block where water is condensed and the rest of the components come as gases. This is the diagram, and it summarizes all the information that we have here. So if you just look at this diagram here, you understand everything. You don't need to go back to the text and read what's there. We will redraw the same flowchart, but with some more information that are given here. So we are told here that the number of moles of nitrogen is 3,660 760 moles per hour, and the oxygen is 1000 moles per hour. Then we have the flow rate of the propane, which is 100 moles per hour. And we know how much oxygen is reacting and how much propane is reacting. And this is the carbon dioxide and the water that's formed. While the nitrogen is an inert, so we know the hydrogen is not changing. So we will draw the same flowchart, but now we have more data that we include here. So we know how much propane is there, how much oxygen and nitrogen is there, and we know how much propane is left. We know 150 moles are consumed per hour, and we have 100, so we'll have 100 left. We know how much oxygen is left, and we know the rest of the components in all the streams. So this is even more informative. It's if you compare this to this diagram, it's almost the same space, but we have more details here or more information here that are summarized in the same space that is also very informative. So you know which information is in which place. So one thing that is very important regarding the definition of the stream compositions and flow rates, and this is what we have here. So we have the stream defined as five components, and each component, we know that stream contains five components, and each component, we have how the flow rate of each one of the five components. So this is one tricky thing, and it causes some confusion, especially for the coming calculation. So I want to make this point clear now that there are different ways that we can use to define the stream. And it's important to know that uh, the information that we put are put in different methods, but it's the same information expressed in different ways. So this stream here that we defined here has five flow rates. So I have five components. Each one of them is defined with its flow rate. Okay. Uh, there is one other way that I can use to define this stream, which is using the total number of mole, which is the summation of all of these, and the mole fraction of each one of them. So if I get the sum of all these components, I get the n total, and if I divide each one of them by the total, it's gonna give me the mole fraction. So if I define this as the total number of moles and the mole fraction of each one of the components, then I am I'm defining the same stream. So it's not necessarily one way that we use to define the stream. It depends on the information that we have. So we can define the stream by defining all the flow rates of individual components or by the total flow rate and the mole fractions of the components. Okay, so the stream composition is defined by sorry, I went back. So the stream composition is fully defined by knowing yi and in total, or the individual ni, the individual number of moles or the molar flow rate of each one of the components. Okay, so this is the same. The information that we have here and here are exactly the same. So here we have some useful hints that I really recommend for drawing flowcharts. One of them is to make the flowchart neat and organized. And this is, it seems a very logical and intuitive thing, but this is something that will come by practice. That you can get this by practice because when you draw a flowchart, you need to make sure that you leave enough space for for writing the data on the streams. You have to make sure that you will be able to connect the streams easily. You don't have a lot of streams that are intersecting. So this is something that comes with practice. The second is to put numbers on each stream, and this is a very important thing. If you look at this flow sheet that you have here, you'll see that we have 23 streams, starting 1, 2, 3, and so on. And these 23 streams are numbered. So numbering the streams is very important because by numbering the streams, you can easily define which stream you are interested in. For example, if I say I am describing or I want to put information on stream 13, for example. So I will easily go to number 13, and now I know that I'm talking about the stream. While if you are you want to, if you don't have numbers, then you need to say that I am interested in the stream, the bottom product of column T106, or the stream that is coming from T106 going to 105. So it gets more confusing if it is a bigger flow sheet with more and more units. But numbering the streams will make it much easier to track the streams and identify the streams easily. So this is a very important hint. Again, we have to leave enough space for writing the data, and always write the units. If there are, of course, if we have dimensionless quantities, then we don't write units, but always write the units of the parameters that you have. If it's mass flow rate, then it has to be in kilograms per hour or kilogram per second or whatever the unit. If it's moles, then put the units of moles and so on. It's very recommended to use symbols instead of words. For example, we use Y for mole fraction, N dot for molar flow rate, M dot for mass flow rate. So symbols are easier to understand and they take less space. And as much as we can, we try to reduce the space that we take for writing text, because it will take a lot of space. So if we can reduce its size, it's gonna be much better and easier for the eye. Uh, uh, the next point is to assign symbol for unknown stream variables. And for example, in the if we go to the previous example that we have here, let's say I have one stream where I don't know what are the flow rates of these components, for example. So I have to put symbols for them, as N for propane, N for oxygen, N for nitrogen. Although I don't know the flow rates, but I have to put them because I need to know what is there. Even if I don't know the quantities or the flow rates, I have to know what is there. And we will see later why this is important. This is going to be very, very, very important later. So this is something that we do this. The last thing is to keep our notations consistent. And if I use a symbol for, let's say, if I go back to this example, or this example, if I use O2 for oxygen, I keep it O2 for all oxygens. If I use carbon dioxide for say CO2 for carbon dioxide, then I keep it CO2 for all carbon dioxide in all the streams. So this is something that is very, very critical, because if you change the notations, then you might think that this is another component. So this is very important thing. So we will stop here and we will continue next time, inshallah. See you then.